Welcome to the next talk by Fabian Immler, who is a PhD student in Munich and ODEsand first group, and is currently in Uppsala working with byWarwick. And he will present his work on ordinary differential equations and so on.
Yes, yeah, so it's about ODE solving, a problem from the area of dynamical systems and ODEs, and mostly formalization and verification work done with the Isabelle theorem proof in higher order logic. A very high abstract level, what is everything about? So for Smale's 14th problem, there was a computer-assisted proof given by Warwick, and this proof involves ODEs. So why would we want to formally verify this? First of all, some of the problems considered to be important, and as it is a computer-assisted proof, so the proof depends on the output of some non-verified C++ program, we gain some additional value by providing a formal proof of the computations. Now, we say, okay, we want to formalize or verify a big theorem. There's a bit the risk of what Sylvie Boldo via Mangueiras described as a Mexican hat. So the danger that you just prove some big final theorem, a lot of specific lemmas which are only of use for this particular theorem, and you have very little general purpose lemmas. And so I claim in this context, this is not the case, because first of all, start from a big library of analysis. We also made some contributions, the library that Johannes talked about. And so the underlying mathematics of the problem is, I would say, interesting. So it's about ODEs and dynamical systems. So here we need a broad foundation. And so the computer-assisted part proof is essentially numerics. So what I also provide is a general purpose ODE solver, so you can use it for any ODE you like. And ODEs are used everywhere for physical systems, biology, chemistry. You can use them to model everything. So this general purpose ODE solver can be used to formally reason about such things as well. And so in the end, the final theorem is like just a small, relatively small application of the existing infrastructure that I built up. Now, first of all, I want to give a bit overview of the problem itself. So I'm going to start with some history. So everything is about, so this is about Smale's problem. So everything is about the Lorenz equations, which have been introduced in the 60s by a theoretical meteorologist, Lorenz, and he used them to model atmospheric flows. So somehow a simplification of model using partial differential equation, which it's a 12-dimensional system, and he simplified it to something three-dimensional system of ordinary differential equations. And he analyzed them by just simulating them on the computer. What I mean by simulating, so it's numerical simulations. So it was computing approximations with like finite precision arithmetic. So there's some theory that tells you when you simulate ODEs, you get something which is somehow close, but no way any rigorous forms or something. What he observed was something quite interesting. Namely, so this is like the evolution of a solution plotted against time, the evolution with respect to one variable, and there's some very regular behavior for a certain amount of time, and at some point get large oscillations. And interestingly, when you do the same simulation with a slightly perturbed initial data, and so Lorenz stumbled upon it at some point when he restarted computations from some intermediate values that he had from a printout, and the data that he used from the printout only correct up to 4 or 5 digits, but the computers would internally compute 6 digits. So restarting somewhere in the middle of the computations actually was slightly perturbed initial data. And it turned out that after you evolve the simulation for a very long time, you get completely different behavior. So, and in the end, the observations that one makes is no matter the slightest perturbation yields enormous differences in the long run. And so this became known as chaos, and also this Lorenz also coined the term butterfly effect in the end, that so give a talk with the title, can the flap of a wing of a butterfly instead of a tornado in Texas. So it's really this to the atmospheric model. Yes, but so despite the evolution plotted along time, it looks somewhat irregular. The structure that evolves when one looks at the evolution in phase space is more or less regular thing. So yeah, this is how solutions behave in phase space and what one observes. But this is still from numerical observations. The structure is chaotic in some sense, strange, and put mathematically precise, I would say that it's hyperbolic. So what's the strangeness about this structure? So all solutions from like everywhere tend towards this structure. So that's why it's called an attractor. The solutions tend towards this structure. But once they are on the or very close to this attractor, on the attractor they will eventually diverge. So with contraction in one direction, like attraction to the attractor, but on the attractor you have divergence or instability. This is hyperbolicity. And so the Lorenz attractor is really famous and been studied a lot because it has many interesting phenomena. And so Sparrow, for example, wrote that the number of man, woman, computer hours spent on the Lorenz equations must be truly immense. Because in some sense it's also like a hello world of numerical numerical computer programs. Any system you have one of the first examples that you implement is the Lorenz equations. But despite all of this effort and study that has been put into the system, there was actually no rigorous mathematical proof that the structure is actually hyperbolic in the rigorous mathematical sense. This is so the only thing where one could make progress was by somehow simplifying the problem. So the attractor, so the mathematical models are, one has good techniques for reasoning about here at the bottom. There's a fixed point of the differential equation. One has good techniques to talk about the behavior close to that fixed point. So there's many local theorems that one can use. But the global behavior, like everywhere else, that is really hard to get information doing classical mathematics. And so this is what led Williams, Guggenheim, and York to define something which is called a geometric Lorenz attractor. So it's a dynamical system. It's defined so cube, where we have the same local linear behavior like in the real Lorenz attractor, and the global behavior is just given by some explicit formula that they chose such that it reflects more or less what the real global behavior is, and that one can prove hyperbolicity. So one can prove many interesting things about this geometric Lorenz attractor, but the connection to the real attractor was missing. And this is something that Steve Smale, so the Fields medalist working on dynamical system, was asked to compose a list of mathematical problems for the 21st century. And one of those problems was precisely the Lorenz attractor, and he asked if the dynamics of the ODEs of Lorenz is the same as the one of the geometric model by Williams before. And I think it's pretty remarkable that it's part of this list. So other problems in the list are, for example, P equals NP, the Riemann hypothesis, Poincaré conjecture, in good company. And yes, but pretty close afterwards, Warwick Tucker managed to prove or to solve the problem, and as part of his PhD thesis. And so the whole idea of this proof is it's very similar to the geometric Lorenz attractor. So everything that one used to prove chaos here is essentially used by looking at the map here on this the top of this cube sigma, and how the dynamics behaves on that on the top of that cube. And so what he was doing is introducing what's called a Poincaré section. So he was studying the behavior on this top of the cube, and the global behavior, like what happens with solutions that stem or that originate from there, which cannot be done analytically. He used called rigorous numerics to produce bounds on the global behavior. So with rigorous numerics, that he enclosed parts of the solution, many tiny intervals, and propagated these intervals such that they would always enclose the real solution. And so he did this in a parallel computation. Back then, 100 CPU hours, and from the bounds that he obtained from this these computations, he could conclude that the behavior is similar to the geometric Lorenz attractor. Actually, that's not everything. So a big part of his thesis is also classical analysis, because so here around the origin, like this part of the geometric Lorenz attractor, this cannot be tackled with numerical methods, because so the behavior of solutions is some solutions tend to this fixed point in infinite time, so there's no way this can be simulated with the computer. So at some point one switches to some symbolic representation, and in this symbolic representation one can analytically reason about the behavior around this fixed point at the origin. So yeah, that's a rough overview of proofs about the Lorenz attractor. So a big part of the proof is based on computer programs. And if you look at Warwick's web page concerned with this thesis, here's some revisions which all correct bugs that he found in the computer program that he used. And some of those bugs are actually there are bugs which were not faithful to the mathematical ideas that you wanted to compute. So it's really it's a difficult task. And so that's why it's worth formally verifying such computations, or these computations. And so the approach that I took is I didn't take Warwick's C++ program and attempted to verify it. I rather implemented my own ODE solver in Isabelle, because doing something from scratch and the idea of formally verifying it is much easier. So I implemented and verified my own ODE solver and applied this to the Lorenz equations. A rough overview of the numerical algorithm that I'm using. So at a high level, it's some sort of reachability analysis computation, and so my idea is that I want to give a bit of a rough idea of the technicalities that I use for proving all those things. So yes, we'll talk about the high-level reachability analysis algorithm, the medium level, like concrete numerical computations with enclosures, and also on a very low level, like what do we do with, in the end it boils down to numeric computations. So what do we do with numbers? On a high level, what is the reachability analysis algorithm doing? So in the end, it's about starting with some enclosure, say perhaps here on this return plane sigma, following its evolution around and see where it returns to this to the return plane. And that's something I plotted here. So it's just an iteration of computing enclosures. Particular for this system, because it's chaotic, this is not sufficient, because at some point, for example, here, the lower part of the phase space, when you get close to the origin, the dynamics of the system will stretch enclosures, because I have an enclosure here. This means there's some uncertainty to the left and to the right, and this uncertainty will be magnified by the just by the dynamics of the system. And so it's to maintain reasonable precision. It's important to just subdivide the enclosures.
Is the enclosure the same as neighborhood?
In this case, the enclosure is some very concrete representation. So Tucker used intervals, and I'm using more sophisticated data structure companies. Yes, so one important ingredient is to subdivide enclosures during the computation, and another one is that the dynamics of the system, as it rotates on some other fixed point, and so the direction of the flow is changing, and so it makes sense to introduce intermediate Poincaré sections. So this is a Poincaré section, and a Poincaré section here means to compute where does the flow pass through such a hyperplane. And this helps in reducing the size of the enclosures and therefore reducing computational efforts, because before the enclosures are wide in the x direction, afterwards this uncertainty in the x directions collapse to 0. And yes, one also needs to certify hyperbolicity. That means this is this strangeness of the attractor. So we need contraction towards the attractor, and on the attractor we need that there is expansion. And this is something one can quantify by talking about the derivative of So this thing here is like a part of the return plane, and if I start with some enclosure in the beginning, let's say I want to study the what happens with some uncertainty in the left-right direction included in this cone between the yellow and blue vector. You can propagate this by computing the derivative of the flow, and if the returning enclosure is closer or is slimmer than the initial one, and I also need to compute like how much would an initial deviation expand, then this helps to certify hyperbolicity or chaos. So in the end, it's the whole program is it's a bit of a, it's a larger program, it's a bit complicated. So I'm using some framework to assist me in the verification of the whole thing. And so I chose to use the Lorenz framework for partly automatic refinement. The idea is that we work the framework with a non-deterministic result monad. So there we can specify programs with first non-deterministic outcome, and this can later be refined towards something executable. Yeah, we have a refinement ordering, so some non-deterministic result S, which is a set of possible outcomes, is fine, and then another one is sets monads, so we have a return. Return is just the deterministic result, then, and we can use this to specify behavior of programs. So specify P means non-deterministically all results for which P holds. And this framework expresses program correctness as a correctness of a program F applied to some for an argument X. If some precondition holds on the argument, then the program refines some specification, which is the postcondition Q.
So what's the semantic difference between the empty result set and fail?
That might just be a technical.
I know of one application which is when you have recursion, then there are two recursion operators, and one of them is essentially for partial correctness and one of them is for total correctness. And the partial one returns the empty result on non-termination, and the total correctness operator returns fail on non-termination. So you can decide whether you want to do partial correctness or total correctness depending on which recursion operator you use, but I don't know if there are other applications.
So, and yes, so then we use abstract specification, so specify the program satisfies just non-deterministically something, and this can then be refined towards something executable. So I have some concrete implementation F tilde, which if applied to a concrete argument X tilde, is related to some abstract algorithm. If the arguments are related by some relation, then the result is related according to some other relation. And so the main parts of the argument can be very conveniently expressed in this framework, because so it's mostly about safe enclosures. So it doesn't really matter what the enclosure looks like. It's just important that the enclosure contains the real result. So, for example, operations to split a set. If I split some set X returns two results, then all this operation has to satisfy is that the union of the two splitted sets. There's an over-approximation of the initial one. To specify an enclosure for the flow, like something that encloses the behavior of the ODE. Also, the result needs to be just something which includes the ODE, and the same for computing a Poincaré map, returning to some hyperplane. And in the algorithm, it's in some sense it's some sort of inference algorithm which Shankar presented this week. So we have some invariant on reachable sets. Sets with the x here, and then with those currently reachable sets, we can do whichever operation, and the invariant will hold, and we just repeat doing either splitting or flowing. Of course, the splitting is guided by heuristics, but that doesn't matter in practice. Yes. So, on a medium level, how do we actually, or what's the idea behind duplication? So, the enclosures, we're not using intervals like Tucker did, because intervals have the problem that when they get, for example, rotated by the dynamics, you need to enclose them. Again, in an interval, this leads to large overestimations. At some point, the overestimations will just explode, and then you get something useless. We rather use sonotopes, which is geometrically it's just it's a sum of line segments. And this representation has the advantage that all linear operations can be represented exactly, and nonlinear operations still incur some linearization error, but this is affordable in this case. And so I talked about these refinement relations. So the refinement framework has some relation sonotopes which relates the set which is represented by some sonotope or by some representation from sonotope L. And so every algorithm that I specified abstractly on just some sets, I can now give it concrete implementations on sonotopes. So, for example, I have a splitting operation on sonotopes, which if the input set is represented by a sonotope, then I get some sets again represented by sonotopes. For doing numerics, the idea is essentially to have an data type of arithmetic expression, which can obviously be interpreted. And so the idea is to do most of the verification on the level of such expressions. So because the interpretation of such expressions, that's still the ideal mathematical entities that we talk about. So for example, interpretation of A plus E, so that yields a real number, which is related to something. And if I want to do rigorous numerics, so the abstract specification is very easy. So if I have some enclosure for the argument, then the interpretation of every point in the enclosure of this expression needs to be in the resulting set. And here again, it doesn't really matter which or what this resulting set looks like. And so one particular instantiation is the approximation sonotopes.
What is the subscript to the double brackets?
That's something like the free variables, or essentially the free variables of the expression, the environment in which the expression is interpreted. Yes.
When the dependency on the environment goes away, that's sort of strange. This universal quantification, I mean, normally you would expect that this R somehow depends on the environment. I mean, for example, if AX is var I. Then for which R should this be true? I mean, you can then plug in
Yeah, I mean,
very funny values.
yeah, but it needs to be something which encloses this var I that's
No matter what
specified.
I is.
Yeah, if you implement it, you need to prove it. So, I mean, yeah, this needs to hold for the input argument x.
So maybe
So-
big X
Oh,
constrains the environments. Is that what's happening?
Yes, so yeah, that's one effect.
So I
Yeah,
thought
for
big
every
X
argument
was
in
the space of all environments, but maybe that is
No,
not
no, no,
true.
it's the argument that I give here. So here I give an enclosure for the environment
Ah, yeah, okay.
and
I see.
the interpretation. So that's how we do numerical computations. In this framework, so we can also do so Euler and Runge-Kutta methods are standard methods for approximating ODEs. Those can be formulated in terms of just manipulating expressions. So the interpretation would be something yeah, more or less Taylor expanding the solution of the ODE. And so this is relatively easy to prove, it's just interpreting the expression. The mathematics to verify such a thing is then a bit more involved. So you need to prove, for example, that the solution, yeah, the difference of the solution with what is computed here is actually contained in this error. And yes, so if we do this rigorously, like using this approximate specification of the Runge-Kutta method on expressions, then this satisfies the specification for flows, so it computes an enclosure for solutions. So another thing, yeah, we talked about derivatives of the flow, which are important to certify chaos. So the idea is starting, we have a solution and there's some initial deviation. We want to know how does this deviation affect the evolution. We could, for example, start enclosing these solutions from there. But it's also possible to, the derivative, to propagate just the deviation and then always gets a linear approximation of the deviation. This is done, so this can be encoded in a higher dimensional ODE. It's called the variational equation. So if the original ODE is from R to the N to R to the N, then this is a matrix of Jacobians, essentially, of the flow, containing all the partial derivatives. So to evaluate derivatives of the flow algorithmically, it's pretty easy. So we just need to describe what the variational equation is. This can again be done like just on the level of expressions. Pretty easy. The mathematics behind is again a bit more involved. So it's to show that the solution to the variational equation is actually the derivative of the flow with respect to space. So these are some non-trivial, but I mean they are standard results in mathematics textbooks, so they require work. So on the lowest level, I mean, in the end, it comes down to computing numbers. The representation that I use are software floating point numbers. So it's for unbounded mantissa and unbounded exponents. So these are mathematical integers. Those are pairs of mantissa and exponent are the basic data structure to perform numerical computations. And yes, of course, if one would just continue doing computations with this ideal representation, then the mantissa would grow because it's just what happens. So I introduced some explicit rounding operations, which are that makes it easy or relatively easy to reason about them, because you can insert them in the code whenever you think it's convenient to reason about it.
But it's still the, I mean, the computational properties that you are still in your close.
Yeah, exactly. So yeah. You insert them at the points where it's obvious that when you round upwards or downwards, it doesn't change the result.
Did you implement this for symbolic numbers? Or? I mean, it was of your own?
No, I think originally Stephen Uber implemented them. I think in the context of FlySpec. Okay, I want to talk a bit about concrete computations. I was doing this verified algorithm on the Lorenz equations. So a rough overview, or also what did Tucker compute actually. So this thing on the right is like part of the return plane here, and so this blue and black thing is a set of interval enclosures, and for every element in this blue set, one needs to do this propagation of the flow and also of the derivatives, and check that when they come back, they return within the set. So in this case, the blue is the initial data, and the black is how like computations returned within the result. Yes, so this blue area is about 300 initial rectangles, and when executing them on a 20 core machine, which is reasonable, this took approximately 155 hours of CPU time, factor of 17 speed up, because like all the initial rectangles you can compute them independently from each other, so no need for synchronization. The problem why it's not a factor of 20 speed up is essentially that there are some initial rectangles which require a lot of work, more work. So the hardest one takes 9 hours.
Can you say again what this means in sort of layman's terms? Like if you go back one slide. So when I have a blue rectangle here, then I guess, so my understanding was that you then take all initial conditions that are within that rectangle and evolve until it again hits this section. So where does it go? Like if I have one blue rectangle, like somewhere, you know,
So
up in
you
the,
see
yeah,
this thing here, that's like this,
yeah,
where this is.
of course. But
So-
when I evolve one of the rectangles,
Yes,
like,
so it
where does
evolves downwards. So
Yes,
if you start
yes.
here, it evolves downwards,
yeah.
and goes there, and
And into
Transfer.
which of the rectangles does it flow? Can I see that from the diagram on the right?
no, you can't see it from the diagram on the right.
So
But
the,
you know,
the
no, it's in the black area.
Oh,
Return is
yes,
the black area.
yes, it's in the black area.
black area, and you don't. The diagram doesn't tell where it goes. So the statement is just that everything that's in the blue goes into the black.
No, you need a bit more.
Ah.
So you also need the information on the derivatives that this matches.
Mhm.
This is somehow similar. And you also need to know, in some sense, where it returns. That's
So
But
this
additional
is a
information somewhere. This
simplification,
is
and the end
simplification.
result is a sort of matching between blue and black air
somehow,
spots
yes.
somehow.
Yeah, yeah.
Sorry, Fabian.
Yeah.
Computations were performed in SML. These
Um,
computations are SML, or
Yes, they are in SML.
And do you not also get this situation that from one rectangle you may go into two different black spots because there's this
Mhm.
chaotic?
Yes, yes.
That can also happen.
I show some examples, I think,
Hmm.
then you will see it. Yeah, so this timing data is when computing the partial derivatives along. If one leaves this out, so this would suffice to just compute this image here. That's roughly a factor of 10 faster. Because instead of a 12-dimensional ODE, you just need to solve a 3-dimensional one. And so, yeah, these are some evolutions projected here from the top and here from the front. And so most of them are easy, they're just a revolution. This is one of the harder ones because it comes closer to the origin, so it's spread out a lot, so there are big sets that you need to propagate. At some point you have something which encloses going to the origin, and at this point, so very close to here, this is where you can't continue with the numerical computations because it infinitely many steps, and there you interrupt the computations, invoke the symbolic form that Tucker also devised in his PhD thesis. Then it's easier again, and so I combined all of this together into one formal theorem. This is an excerpt from Tucker's article about what he's actually computing, and so I try to phrase this in Isabelle. So see, it's about the return map which needs to exist. So if n is this blue area I was talking about, so every point in the blue area returns. R is the return map, needs to be closed there. R has a derivative. The derivative is a whole field is mapped into itself, and then also some expansion bounds on the derivative. So the norm, the derivative needs to be larger than something. And so in principle, and this is something I haven't done formally because it still requires some theory of dynamical systems, you can deduce from all the information that we have here about the expansion and the derivative and the return map, you can deduce that this is a hyperbolic system.
So where is the effect that you have some conditions on the origin?
This is here if normal form correct.
Ah, okay.
So this is the theorem that you need to invoke when you need to switch close to the origin. And yeah.
Can you express that there's an attractor? Can you say what an attractor is?
You mean formally?
Yes.
Currently, so in Isabelle, currently, no. So this here is an attracting set. An attractor means that the attracting set is in some sense indecomposable. So, and this is something we prove with the help of the derivative and the expansion estimates.
Yeah, my question was, so you don't have that?
No, it's not formally in Isabelle. That's about it. Questions?
So when you certify a program, you can always have some part of the computations that will not be certified, like for instance strategies for deciding, I don't know, where to split something. Is there something like this in your code? Part as some kind of code which could be in principle implemented in some kind of external tool that would drive what is in the code?
I think that's what I try to hint at here. So we have some operations like splitting or flowing or doing the concaret map, and so you're doing these in a loop, but the decision on what to do, that's something heuristic, and so that's currently implemented in Isabelle, but I don't need to prove anything about it.
But we
So there I could use some external
do you
oracle.
think it would help with the efficiency or it's just negligible?
Perhaps a bit, but I don't think you would gain more than a factor of 2.
So the related question is, where are you slow compared to other implementation architectures? Where do you pay costs? Arithmetic?
I think doing arithmetic with these software floating point numbers, that's, I guess, should be around a factor of 10 against hardware floating point numbers. So there you lose a lot, and I never really tried profiling or optimizing things.
Does Tucker also use hardware floating point?
Yeah.
Ah, okay.
So you proved the computations, but not yet the whole proof.
Yes.
Have you proven the behavior close to the origin?
No. That's, I would say, that's the hardest part.
Okay.
Yeah, you said this with the Mexican hat, that your development can be used for other things. So do you have anything in mind, like other theorems that one could attempt with the scaffolding that you have developed?
So I don't have a concrete theorem in mind, but I mean, it can, for example, also be applied to cyber physical systems. So yeah, this year I participated in a software competition for analyzing cyber physical systems with this tool.
What did you have to do there?
It was just about computing enclosures for the behavior of some systems.
Well, do tell us how well you did.
Yeah, actually not too bad. So on a very simple example, like a two-dimensional system, runtime and performance was on par with other tools. So some were faster, some were slower. Everything, I don't know, around 10 seconds, plus minus 10. And
In 1 hour, or
what?
so? What was the entire runtime of the? So if it's 10 seconds plus minus, and the runtime is 3 seconds, or 15 seconds.
Oh no! I mean the total runtime is about 10 seconds.
Ah, okay.
And yes, for a more complicated example, it was a factor of 20 slower than other tools.
But the other tools don't give a certification.
No, they don't give a certification.
Do they give the same result?
Mostly.